Metropolis-Hastings is a random walk where the Markov chain is never explicitly constructed. If a stationary distribution exists, then law of large numbers says if we run the random walk infinitely, then the probability of being in a given state in the chain is equal to the probability of that associated sample, which is what a probability distribution is. But how do we know that this stationary distribution is the same as our target distribution? They are the same if detailed balance can be satisfied. At each step in the chain, a new state is proposed and either accepted or rejected according to a dynamically calculated probability, called the acceptance criteria, or alpha. So we rewrite detailed balance as the product of target distribution, proposal distribution, and alpha, rearranged as A over Fg, and let this fraction equal lambda. There is a trivial solution where acceptance probability is minimized to 0, so lambda will be 0. If multiple solutions exist, then we want lambda to be maximized. Rearranging detailed balance as a ratio of A, F, and G, Metropolis-Hastings has two cases: random walk towards lower density or not. From Metropolis-Hastings theory, if proposed density is greater than or equal to current, we accept it with probability 1. The other case is calculated to meet detailed balance. Given one of the steps must have acceptance probability 1, we maximize lambda by selecting the maximum value from our set of two possible cases. Since distributions are never negative, we know our terms are positive. For any two positive fractions, the larger fraction will have a smaller inverted fraction. Metropolis-Hastings cannot propose a step with 0 probability, so divide by 0 error will never occur. Combining our equations, we can now solve for alpha by multiplying denominator and distributing. Suppose we have a target multivariate PDF in d dimension. Instead of proposing a new location for all dimensions simultaneously, as in multivariate Metropolis-Hastings, Gibbs sampling factors the multivariate target distribution into d univariate conditional distributions, one for each of our d dimensions. Let us now show that the random scan Gibbs sampling is a special case of Metropolis-Hastings where the proposed moves are always accepted, that is, acceptance probability is 1. Random scan Gibbs sampling repeatedly samples from the conditional distribution of one random variable of the target distribution P given all the other variables. Let x sub I denote the ith variable, and let x sub negative I denote the set of all variables except x sub I. Let Q be one of our univariate conditional distribution that is random uniformly selected with probability 1 over d. In order to sample from any univariate conditional distribution, we must first select it with probability 1 over d. Gibbs sampling assumes we can compute conditional distributions of one variable conditioned on all the other variables and sample exactly from these distributions. Y is the proposed vector equal to the ith proposed variable given set of all other variables. We have not yet moved there. X is the current vector equal to the ith variable given set of all other variables. Pi is normalized target distribution evaluated at some feasible conditional vector equal to the joint probability form of the same feasible vector. Substitute feasible vectors into proxy distribution. We plug our random scan Gibbs sampling variables into Metropolis-Hastings acceptance criteria. Solve for alpha by rewriting joint as conditional. This shows random scan Gibbs sampling is a special case of a Metropolis-Hastings where proposed moves are always accepted, that is, acceptance probability is 1. The deterministic Gibbs sampler uses a for loop that goes through all the variables in some order and samples x sub I of the next step from the conditional distribution of x sub I prime given all the other variables. The deterministic next sample is selected in d steps as shown. Since Metropolis-Hastings satisfies detailed balance and Gibbs sampling is a special case of Metropolis-Hastings, Gibbs sampling satisfies detailed balance.